Hello everyone. The title of this video is Section 8.2, Part 1. Use the product property to simplify radical expressions, right, or simplify roots. So in this video, I'm going to be going over a version of the Knewton Alta assignment for Section 8.2, Part 1. Please understand that the version I'm going to be looking at in this video may or may not have the same questions that you are going to see when you work on the assignment on your own. But the objectives will be the same, the kinds of questions will be similar, and the way you would go about doing them is similar to the way I will do them. So hopefully watching me do this will help you in some way when you're working on the assignment on your own. And one other thing I request of you is that when a new question comes up, try to work on it yourself first before watching me do it. Because if you're just watching me do these things and not practicing yourself, chances are you're probably not learning much of anything. Alright, so here we are on the assignment page. Now you will not see the words preview of. Right, you're just going to see the title of the assignment, the mastery bar, right, telling you how far along you've gotten, the objectives. Now it looks like this assignment here has just the one objective. Then at the bottom of every question there should be a feedback button for which you can give feedback to Knewton, and you'll see a more instruction button. Right? You will not see the instructor cheat button. That is for instructors only. And I highly recommend the use of the more instruction button if you're struggling. If you click on it, you should be opening up to a page with reading material or videos that'll hopefully help you with whatever objective you're working on. Alright, so this first question, as with all the questions in this assignment, right, there's only the one objective. Use the product property to simplify radical expressions. Alright, so I'll state this product property for you, as we go through these questions. So the first question, we're asked to simplify the square root of d to the 23rd power. Alright, so I'll write that out and do it on some piece of paper. Alright, so first we're asked to simplify, right, using, we're going to be using what's called the product property for radicals. And I'll write out this product property over here. So the product property for radicals states the following. Right? So you have, here's the radical symbol, and remember the index, so this is the nth root, right? I put the letter n there, and if it's not there, right, if there's no number here, remember that's the square root. And suppose the radicand is a product, say some expression a multiplied by some expression b. Well, this would be equivalent to the product of the nth roots of each factor. You can take the nth root of just the first factor, a, and multiply by the nth root of the second factor, b. Right? And if there were more factors in here, you could keep breaking it up. Now this is only true as long as these are real numbers. As long as the nth root of A and the nth root of B are real numbers. And if you recall back in section 8.1, when we did even roots, right? If n was even, the square root, the fourth root, the sixth root, the eighth root, etc., then the radicand couldn't be negative, right? The radicand, if the radicand was a negative number and you had an even root, that was not a real number, right? But if the radicand is not negative, then you'll have a real number, right? So you can use this property, right, as long as these two numbers here, these two radicals, are real. Right? So really you just have to pay attention when you have even roots. Because if you recall, when there was an odd root, right, a cube root, fifth root, seventh root, etc., it didn't matter if the radicand was positive or negative. Every real number had a real odd root. Right? It was just for the even roots that you really had to pay attention. Okay, so here's what we're going to do. When we're simplifying, now notice that this is a square root. Right? In other words, the index is 2. What we're going to do is we're going to rewrite our radicand as products of perfect squares and non-perfect squares for a square root. If it were a cube root, I'd rewrite it as a product of a perfect cube and a non-perfect cube. So first I'm going to rewrite the radicand, right? That's the expression underneath the symbol, as a product and multiplication of a perfect square, and again this is for square roots only, right? Perfect square times, not a perfect square. Alright, so remember perfect squares. Alright, I'll do this off to the side. Perfect squares are just any expression that can be, written to the second power, really. Whole numbers squared, variables squared. So basically, if you have a power that's even, you have a perfect square. 1 squared is a perfect square. Then 1, 2 squared is a perfect square. That's 4. 3 squared is a perfect square, right? That's 9. Those are numbers that are perfect squares, 1, 4, 9, and so on. But perfect squares can also be expressions, x to the second, y to the second, x to the fourth, right? Because that's x squared squared, right? Something's squared. X to the sixth. This is x cubed squared, right? Basically, if you have an expression with an even power, these are just expressions with even powers, 2, 4, 6, 8. And the expression doesn't have to have just a single term like x here. I could have x plus 1 to the 8th power. Right? There's a perfect square because this is x plus 1 to the 4th squared, right? And so on, right? So anything really that has an even power, an even exponent. All right, so going back here, right? This d to the 23rd. That's clearly not an even exponent. Right? I'm going to take the radicand here. I'm going to take this d to the 23rd, and I'm going to break it apart. I'm going to write it as a product of a perfect square and not a perfect square. All right, and what I want to do is find the largest perfect square that goes into the radicand evenly. So that would be d to the 22nd. Right, the perfect square, the largest perfect square that goes into d to the 23rd would be d to the 22nd. And then times, and then, all that's left over is a factor of d to the first. There's your not perfect square, right? D to some power that's not even. So I have perfect square, right? D to the 22nd, which is, d to the 11th squared. And then your times a not perfect square, right? Just d to the first, d to an odd power. Okay, so we have now the square root of d to the 23rd, and then I break it up using now I'll use the product property. Right, use the product property for radicals. Well, if d to the 23rd is d to the 22nd times d, then the square root of d to the 23rd is equivalent to the square root of d to the 22nd times the square root of d. Now I hope you recall from section 8.1's video that the nth root of something to the nth power was equal to the absolute value of that thing if n was even. Right, when you took an even root. Right? Because when you see this symbol, right, when you see an even root symbol like square root symbol here, remember your result there, that symbol means the principal even root, the positive one, the non-negative one. So your final result can't take a negative value. That's why the absolute values are there. So and you saw this back in 8.1, section 8.1. The square root of d to the 22nd would be d to the 11th, but with some absolute value symbols around it. The reason being is because d to the 11th, this can be negative if d were negative. But I don't want this to ever be negative, right? Because again, this symbol tells me we want the principal or the non-negative square root. So I'm putting absolute values around d to the 11th. Right? They must be there. We must ensure that our result is the principal square root or the non-negative square root times and then the square root of d. Right? And that square root doesn't simplify any further because there are no more perfect squares as a factor. And this is what I'm going to type. All right. Now for this example, right, I was writing the radicand as a perfect square times, not a perfect square. If this were a cube root, right, if this had an index of 3, I'd be writing the radicand as a perfect cube, right, where my powers are, the power is a multiple of 3 times a not perfect cube, and then using the product property. Right? And with odd roots, remember with odd roots, you don't need to worry about absolute values. Right? You don't need to worry about having the root be the principal even root. Right? Odd roots can be anything. Odd roots can be positive. Odd roots can be negative. Alright, so this is what I'm going to enter. Don't forget the absolute value symbols. Right? So back here, got an absolute value right here. Then we have d to the 11th power inside, and then outside we have times, the square root of d. And there we go. That should be good. And after every question, there should be an answer explanation. whether you're right or wrong. Please read this. Please read these. If you're correct, just glance through it and make sure that you are correct for the right reasons, right? That you didn't just get lucky. Or, they may have done it in an alternate way that you didn't think about that you might like better for future questions. Now, if you're wrong, definitely read through the answer explanations and see if you can figure out why you went wrong. Right? And maybe you'll learn from your mistakes for future questions. Alright, so the next question, same objective. Another square root. Right, another square root. So again, square root. So I'm going to break up the radicand into a perfect square times a not perfect square. And I want to pull out the largest perfect square possible from the radicand as a factor. All right, so once again, I'll write this out, and we'll start factoring 140 times c to the 31st. Okay. So let's look at the radicand. Right, 140 times c to the 31st. I am going to factor 140 completely. Now if you want to do a little factor tree, that'd be fine, right? This is 14 times 10. 14 is 2 times 7, and those are prime. 10 is 2 times 5, and those are prime as well. So 140 is 2 squared times 7 times 5, or times 5 times 7. Right, 4 times 35 is 140. And then c to the 31st, just c to the 31st for now. Alright, and like I said, we're going to factor, I'm factoring the radicand and trying to break it up. I want to break it up to perfect square times non-perfect square. Right. So, 2 squared, if any of the powers are higher than 2, then you have perfect squares that you can pull away. 2 squared is a perfect square, so I'll write that down. 2 squared times. Now 5 to the first, you're not getting a perfect square out of that. Same thing with 7 to the first, right? You're not getting a perfect square out of that either. C to the 31st, right? The largest perfect square that goes into that would be c to the 30th. Right. So here are the perfect squares. And once again, this is only because this is a square root. That's why I'm looking for things with powers that are multiples of 2, right? Things that are squares. If this were a cube root, I'd pull out, powers that were multiples of 3, right? And if it were a fourth root, I'd be factoring out, powers that were multiples of 4. So please pay attention to what root. I think most of these will be square roots. So I've got 2 squared, c to the 30th. All right. So what will be left over will be the not perfect squares. And we have the 5. I did 2 squares, so there's no more 2's. And we got 5 times 7, right? So times 5 times 7. And I pulled away 30 factors of c. That leaves me with 1 factor of c. Right? Okay. So I've broken it up to perfect square. I factored the radicand to perfect square times non-perfect squares. And then we use the product property. This square root of 140 c to the 31st is the square root of 2 squared, and you know what, I can break it up even more, times c to the 30th. Right, there's the perfect squares inside 1 times the square root of the non-perfect squares. Now 5 times 7 times c, that's 35c. Right, I'll just leave that the way it is. The non-perfect square radical won't simplify any further. And then this radical you could break up even more using the product property, right? This would be the square root of 2 squared times the square root of c to the 30th if you want. Right? You can do any product and break it up using that product property. Then I have times the square root of 35c. Now, the square root of 2 squared, that's just 2. Technically, it's the absolute value of 2, but the absolute value of 2 is 2. Right? So there's no need to write absolute value around this. It's already positive. Times the square root of c to the 30th, right? That'd be c to the 15th. Because c to the 15th to the second would be c to the 30th. But this can be negative though, can it? This c to the 15th, this can be negative for negative values of c. So once again, to ensure that I'm getting the principal square root, I put absolute value symbols around that root, around the c to the 15th. So now I have 2 times, the absolute value of c to the 15th. So now we're still positive, right? Still non-negative, times the square root of 35c, right? The non-square root, the non-perfect squares. And that is as simple as it gets. Okay. So that's what I'm going to enter. Again, be aware that you are going to have to use, for even roots, right? Square roots, fourth roots, sixth roots, right? You're going to have to be using the absolute value symbols at some point. So 2 times the absolute value of c to the 15th power, and then after that times the square root of 35c. Great. And again, please read through the answer explanations. Alright, next question. Same stuff. Just got to pay attention to if you have a square root or a cube root or a fourth root. And again, here it's a fourth root. Aha. So when I do my factoring, I'm going to look for powers that are multiples of 4. Right? Any powers higher than 4 tells me I can pull out a perfect fourth power. Alright. Alright, so this is now a fourth root, right? So that means we're going to look for perfect fourth powers, not perfect squares. Now, perfect fourth powers, those would have exponents, powers that are multiples of 4, 4, 8, 12, 16, and so on. So I'm going to take the radicand again, 405 times, x to the 7th. And I'm going to break up 405, right? Now 405 is clearly a multiple of 5. That'd be 5 times 81. And 81 is 3 to the 4th. Alright, it's 9 times 9, and both those 9s are 3 times 3. So what we have here is 3 to the 4th times 5, right, that's 405, times x to the 7th. Right, and then I look at all these powers. Since it's a fourth root, I'm looking for powers, after breaking it up completely, I'm looking for powers that are higher than 4. 4 or higher. 4 or higher. If any of the exponents are 4 or higher, that means I can pull out a perfect fourth power. Right, like 3 to the 4th. That has a power that's a multiple of 4. So I can pull that away. Now 5 to the 1st, I can't pull out 4 factors of 5 there. I can't pull out a perfect fourth power with the 5s. X to the 7th, I can. Right? 7 is 4 or greater, and you can pull away x to the 4th. Right? There's another perfect fourth power. And that would be it, right? So here are the perfect fourth powers. Alright, so I'm gonna rewrite this as a product of perfect fourth powers, and then the rest of it will be, not perfect fourth powers. Well, the rest of it, I mean, 3 to the fourth, I've already used all factors of 3 here. There's still a 5 to the first left times, and then I've used x to the fourth, right? 4 factors of x, and there would be 3 left, x cubed left, all right, making the x to the 7th. All right, so then I can use the product property. This would be the fourth root of, 3 to the fourth times x to the fourth, right? Times, I put my perfect fourth powers in one radical, times, and then the non-perfect fourth powers, right? The fourth root of 5x cubed in the other one. Okay, then if you'd like, you can break this up even. All right, this would be the fourth root of 3 to the fourth times the fourth root of x to the fourth times, and then our fourth root of the non-perfect fourth powers. I'm going to leave the non-powers, the non-perfect powers in their own radical. And then we simplify. Now the fourth root of 3 to the fourth power, again, this is even. Right? Remember the even symbol, even root. The result can't be negative. Well, the fourth root of 3 to the fourth is just 3. Right? Technically, I would write the absolute value of 3, but the absolute value of 3 is just 3, which is already not negative, right? So I'm good with just 3 there. The fourth root of x to the fourth, now if you write just x, you'd be incorrect. Again, this is an even root, so they want the principal even root. The result can't be negative. Well, if you write just x, x can be negative. That when x is a negative number. So once again, put absolute value symbols around that to ensure that we get the principal square root, the positive one, the non-negative one. And then I have times that fourth root of the non-perfect fourth powers. All right, and this is it. This is as simple as that would get. And that's what I'm entering. Again, don't forget for these even roots, chances are you're going to be using absolute value symbols at some point. So we have 3 times the absolute value of x, and then after the absolute value we have, now this symbol here has the area for the index because I need to put a 4 for the index, so I times the fourth root of 5x cubed. All right, and that should be good. Great. And once again, please read through the answer explanations. All right, and I should have just one more here. All right, so it looks like another, oh, this time it's a sixth root. All right, now I know that every question in this video has had an even root. So I needed absolute value symbols. I needed to ensure that the final result was not negative. Please be aware that you might come across odd roots, right? Cube root, fifth root, seventh root. Just pay attention. Now with an odd root, right? Cube root, fifth root, seventh root, the result doesn't need to be positive. You don't write absolute value symbols, when simplifying an odd root. All right. So once again, write this down. We'll work on it. So this is a sixth root. So I'm going to take the radicand and I want to write it as a product of sixth powers and non-sixth powers. Right. So the way I would do that is x to the seventh is x to the sixth. All right, that's a perfect sixth power. Right? Anything with an exponent that's a multiple of 6, right, to the 6th power, to the 12th power, to the 18th power, would be a perfect sixth power. Times, and then some, the factors that are not perfect sixth powers. Well, I already used 6 of the factors of x. There's only one left. And I'll just put, not here. That's not a perfect sixth power. Alright, so now I've broken it up to the way I want. Again, you gotta pay attention to the index to tell you what what you're breaking it up into, perfect what power and not perfect what power. Then the product rule, right? I'm gonna break this up to the 6th root of the perfect sixth power, right? X to the 6th times, and then the 6th root of the rest of it, right? Just x. Then we simplify. Now the 6th root of x to the 6th, again, if you write just x, you're wrong. Right? This is once again an even root. So the result needs to be always non-negative. And this is not always non-negative, right? If x were negative, this would be a negative value. So once again, to ensure that we get a non-negative result, I take the root and then pop some absolute value symbols around it. And once again, this is you're only doing this for even roots. Odd roots, you don't need to worry about that. Times and then the 6th root of x, right? That root with the non-powers in it, right? The non-perfect powers, just leave it the way it is. Right? So here is what I'm going to enter. Right? The absolute value of x multiplied by the 6th root of x. And again, you use this symbol here that has a place for the index, because I need to enter an index of 6. 6th root of x. Great. And once again, please read through the answer explanations. Alright, now I know every single problem here in this video had an even root. Once again, I'll say, please know that you may come across questions with odd roots. So if you had a cube root, you would do the same thing, right? You'd break it up into perfect third powers, with powers that are multiples of 3, 3, 6, 9, 12, and so on, times, and then, not perfect third powers, and then break it up using the product property and simplifying. All right, and you wouldn't have to worry about absolute value symbols with a third power, with an odd power. All right, and that should be it for this version of the assignment. And as I've been saying a lot, right, the version you see when you work on the assignment yourself will probably have different questions than the one I just did here. Right, you may have some odd roots showing up, but again, the way you do them is the same. The way you do them, it would be similar. The objective's the same. Everything else is the same. Right? It's just the questions might be different. So I'm hoping watching me go through at least these 4, help you in some way, and maybe other videos I've put out help you in some way when you're working on the assignment on your own. And thank you very much for watching.